Okay. Okay. Now it's time, I think. So first of all, hello to everyone. I'd like to introduce you, Noa Zilberman. She's a doctoral student in Israel Institute of Technology under the supervision of Professor Amos Ovi. She recently published some very interesting research result on the effect of quantum fields in the charged and the rotating black hole background, including a couple of papers published in Physical Review Letters. Personally, actually, I'm very interested in the method to regularize the expectation value of the stress energy tensor near the Cauchy horizon, and the sign change of the flux component of the denormalized stress tensor of the field near around the Cauchy horizon, depending on the polar angle for given ratio of the spin and the mass of the black hole. And please, Noa, take the stage, and all yours.
Thank you very much. Thank you for inviting me again. It's a great pleasure to give this talk. So today we'll talk about semiclassical energy fluxes at the inner horizon of a rotating black hole. So I will start with a short story with an open end. The analytically extended Reise-Nordström and Kerr metrics, describing respectively spherical charged or spinning black holes, reveal a traversable passage through an inner horizon to another external universe. And this remains the case in the more physically realistic scenario of gravitational collapse, in which only the ingoing section of the inner horizon maintains the role of a Cauchy horizon, being the domain being the boundary of the domain of predictability for initial value problems formulated outside the black hole. So that's what we call the Cauchy horizon. And now imagine a traveler in our universe intending to access this other external universe. In order to do so, she must pass through the black hole interior, and in particular through the Cauchy horizon. What will she encounter along her way? Is her mission doomed to fail, and does this other external universe actually exist? So in order to answer these questions, one would need to understand the manner in which quantum effects modify the geometry inside black holes. And in particular, that would require the computation of the stress energy tensor on the Cauchy horizon. So in this talk, we'll start with motivation and basic framework. We'll talk about the Unruh quantum state, which is the state that we consider. Then we'll see what is the individual mode contribution to the flux components of the stress energy tensor. We'll talk about the renormalization method via state subtraction. We will construct this state and see what it gives us. And then we'll see some numerical results, as Professor Hall already mentioned. And finally, a very short and preliminary discussion of back reaction. So let's begin. So it's not a new thing that quantum effects may change drastically the space-time geometry. And of course, the most famous example is Hawking radiation, already known from the 70s. But already on the classical level, it is known that classical perturbations change the otherwise regular black hole interiors, in particular at the Cauchy horizon, introducing a weak singularity there. It has been shown both in the spinning and charged cases. So it is a question we would like to ask, whether the quantum perturbations will have a stronger singularity effect at the Cauchy horizon. And there have been some analytical studies supporting this expectation. So this is what we are interested in, to tackle this problem in the numerical level and actually compute things and try to give a question, to give an answer to this question. So we started with the spherical charged case, in which there are some recent results by us in the asymptotically flat case, and by Holland's group in Leipzig in the De Sitter case. And our goal, the goal of this current work that I'm going to talk about, is to address this issue in the rotating case in a concrete way. Because the rotating case, of course, is a more physically realistic case. So because we are interested in the way that quantum effects change the classical space-time picture, we are going to use the semi-classical formulation of general relativity, which treats quantum matter fields as propagating on a classical curved space-time, and they obey the semi-classical Einstein equation. So on the right-hand side, we have the renormalized expectation value of the stress energy tensor related to the quantum field in question. So because of the curvature of space-time, we're going to have non-trivial contributions to the right-hand side. And these, in turn, through an effect known as back reaction, may change the classical space-time picture. So this very involved equation poses a requirement for self-consistency. But already on the very first level, just computing the renormalized stress energy tensor on the right-hand side on classical static or stationary black hole background, it is already very, very hard because of the very subtle nature of the renormalization procedure. So this is what we want to do. Okay, so first I'm going to introduce to you the classical black hole background, and then the field. So the background metric that we consider, we first considered Reiser-Nordström because it is simpler. It corresponds to a charged black hole, and then we considered the Kerr metric, which is more physically realistic, but it is also harder because it doesn't have spherical symmetry, and it corresponds to a rotating isolated black hole. So I decided to start with Reiser-Nordström just because it is something that is more familiar to people. It looks like Schwarzschild, but this function is different, and that means that it has an inner horizon, and we're going to use EH and IH for the event horizon and inner horizon. And this is the Penrose diagram of the maximally extended non-extremal Reiser-Nordström black hole. And the Kerr metric has this dphi dt term, and it also has an event horizon and an inner horizon, just like the Reiser-Nordström metric. And they are given by these equations, these expressions, where A is the angular momentum per unit mass. So this might be all very familiar to you already. So we are going to be interested in this red frame. The exterior universe is what we call everything between the past-null horizon and the event horizon. And the black hole interior is up until the inner horizon. So this is the red frame that we'll be interested in. Okay. So the Reiser-Nordström metric has a surface gravity. It has a R star coordinate with which we can define the Kruskal coordinates, which are regular at the horizon. And similarly, in Kerr, we also have surface gravity. Just note this A squared over here. And we are using the R star coordinate to construct Kruskal coordinates just in a very similar way to the Reiser-Nordström metric. But in Kerr, for all infalling observers, dphi to dt has the same asymptotic value, which is this capital omega over here, plus for the event horizon, minus for the inner horizon. And because t diverges at the horizons, phi also diverges there, so we have to introduce phi plus for the event horizon, phi minus for the inner horizon, which are regular at the horizons. Okay, so that was just a recap of the Kerr metric, because I'm going to use these parameters. And now the field. What is the field, the quantum field that we are going to consider? We are considering a minimally coupled massless scalar quantum field, which obeys the simple Klein-Gordon equation. This is the covariant diversion. And the Tucholsky equation, also called the master equation, on a Kerr background, has this form. The form itself is not so important. What is important is that it can be decomposed. So that is very useful for us. The solutions to this equation can be decomposed to temporal, radial, and angular terms. The temporal factor has omega, which is the time translation frequency. This is going to be important when we talk about the modes. The angular term is the spheroidal harmonics rather than the spherical harmonics, because we don't have spherical symmetry, and they have these spheroidal eigenvalue corresponding to them. And because of this division by the square root of r squared plus a squared, this radial function psi obeys a Schrödinger-like equation. So this v over here, the potential in this equation, involves omega, the frequency, in a non-trivial way. It also involves the angular eigenvalue. So I'm not going to give the potential, but interestingly, it has different asymptotic behaviors at the different asymptotic domains. It's either omega squared, omega plus squared, or omega minus squared at the inner horizon, where this omega plus and minus are defined using this capital omega that I showed you before, the asymptotic value of d phi to dt of infalling observers. So outside the black hole, the potential behaves as a potential barrier, and inside as a potential well. That's very roughly speaking of the radial equation, just to give you an idea. Okay, so now that we know what we are talking about, what is the problem that we want to solve, what is the background and what is the field, we are going to talk deeper about the Unruh quantum state. So as I said, our field is just a scalar quantum field, and we are considering it in the Unruh state, which corresponds to an evaporating black hole. Again, this is a choice that we do because it is more physically realistic. So in order to define the Unruh state, we first decompose our scalar field in terms of Unruh modes. So this lambda over here is either up or in. We have in Unruh modes and up Unruh modes, which we are going to describe just now. And then the Unruh state is defined this way. So it is annihilated by all the annihilation operators that appear in this decomposition. And the Unruh state is defined through this red frame that I traced before. So the Unruh up and in modes. Let me just remind you the coordinates. We have Eddington coordinates, which are linear in t, and Kruskal coordinates, which are not. And that is important because that means that for every frequency with respect to Unruh coordinates, it is going to be a time translation frequency, because for every frequency with respect to v, Eddington, there is one frequency with respect to t. But in Kruskal, it's not going to be the case. So the in Unruh modes are defined by incoming from past null infinity with respect to the Eddington v. So that means that they are decomposable in the usual sense, again, because v and is linear in t. But the Unruh up modes arise from HL and H past with this behavior with respect to the Kruskal U. So this omega hat over here, it does not correspond to a single time translation frequency. unlike the Eddington that we had here. So that means that the Unruh up modes are not decomposable in the Tucholsky sense that I showed you before. So that means that in order to solve for them, we will have to solve a PDE and not a nice simple ODE like the radial equation that we saw in the previous slide. And that's why we also define the Eddington modes. So we just define them for convenience. It's a mathematical tool in a way that they will be separable. So this psi over here is just the radial function we saw before that solves the radial equation, which is just a Schrödinger-like ODE. So we have exterior Eddington modes, which are defined in the black hole exterior, and both of them arise with respect to the Eddington coordinates on these asymptotic surfaces. And the interior Eddington modes, so the left one arises from the left arm of the event horizon, and the right one, FR, arises from HR, the right arm of the event horizon. And again, they arise with respect to either V or U Eddington, and with omega plus, but this doesn't pose any problem because omega plus is also linear in omega. So for every for every omega plus here or here, we have a single time translation frequency. So these are decomposable in the usual Tucholsky sense. So that's convenient. So we, so here I say that for more details on the different families of modes and how they are related, we wrote a paper which was recently published in PRD. It's pretty long, but the bottom line is that we can decompose every Unruh mode in terms of Eddington modes, and then we can make our computations easier. Okay, so now let's talk about the mode contribution to the fluxes using the computationally favorable Eddington modes. So we start by just describing the stress energy tensor in minimal coupling. So our classical starting point for a scalar field would be this expression. And it is comfortable to use the trace reversed version, which we denote by a different T over here, which is just the product of these two field derivatives. Now, naively, we just say that the quantum version of this classical expression would be just to put expectation value on both sides. But of course, this diverges, so we'll talk about that later. Now, again, because of the curvature of space-time, there are flux components in space-time. What are the flux components? These are Tuu and Tvv, where U and V are the Eddington coordinates inside the black hole. And it turns out that these Tuu and Tvv are crucial for back reaction at the Cauchy horizon vicinity. So just let me note that because the Unruh state, as I said, it corresponds to an evaporating black hole, and in particular, it is regular at the event horizon. Because it is regular at the event horizon, that means the Tuu in Eddington coordinates has to vanish there, because otherwise, transforming to Tuu in Kruskal coordinates, these ones, which are regular at the event horizon, we will have something that diverges. So that wouldn't agree with the regularity at the event horizon. So just like Tuu has to be 0 at the event horizon for regularity, if we have non-vanishing Tvv at the Cauchy horizon, that would mean that we have a singularity there. So just keep that in mind. Okay, and another nice fact is that energy momentum conservation in the Kerr metric yields a conserved quantity, which is r squared plus a squared times the difference between Tuu and Tvv for a particular theta, for a particular direction. and this is independent of r, and if we take it to infinity, it coincides with the Hawking radiation outflux per unit solid angle in that direction. So Tuu and Tvv are related by this conserved quantity. Okay, so as we said before, we start with this naive bare trace reversed stress energy tensor, which is related to the stress energy tensor in this way. And now we want to take it to the event to the inner horizon, where we are interested in computing things with yy, which is either u or v. That is, we're interested in the flux components that I showed you before. So Tuu or Tvv at the inner horizon, which I denote by minus here, will be just this very simple expression. Again, this is just the bare or naive expression. And this is because Tuu and Gvv vanish at the inner horizon. So this term vanishes. Okay, so that's the bare inner horizon flux components. And we focus on Tvv. As I said, Tuu is related by a conserved quantity. So Tvv at the inner horizon in the Unruh state will be equal to this product of field derivatives in the v direction. And in terms of Unruh modes, it is very easy to get to this expression, just using the definition of the Unruh state and the decomposition of the scalar field. Now, as I said, each Unruh mode may not be written as a single Eddington mode, but as a superposition of Eddington modes. So when we do that, and we take the asymptotic form of the radial function at the inner horizon, we reach this expression. So this is a mode sum, the mode sum expression for the bare contribution to Tvv at the inner horizon. And it is composed of A and B, which are the interior translation coefficients. The interior translation reflection coefficients, and rho up, which is the exterior reflection coefficient for the radial function. Okay, so this is the expression we got. A and B are defined this way through the asymptotic form of the radial function at the inner horizon, and rho is just the very standard scattering coefficient for the up mode outside the black hole. So that looks like quite a nice and simple, well-defined and well-computed expression. But the problem is that the sum diverges. So for each mode, we have the contribution, we have all the required information, but when we sum and integrate, it diverges. So now we need to renormalize. Okay. So generally speaking, when we want to find the renormalized expectation value of the stress energy tensor, we start with the bare mode sum, which I just given you before, and we subtract the diverging quantity that needs to be subtracted. And importantly, it is purely geometric and it is shared by all quantum states. So that means that if we take two different quantum states, let's say Unruh and some other quantum state, let's call it Q, we can subtract this equation for both of them, and then we get something that doesn't depend on the diverging quantity at all. We have that, let's say in Unruh state, the renormalized stress energy tensor would be equal to the difference between the bare stress energy tensors, the bare, in these two quantum states, and we just need to add the renormalized stress energy tensor in the other quantum state. And this is just regular. It's supposed to be a very feasible thing to compute. But again, it is only useful if this is known, if the renormalized stress energy tensor in the other quantum state is known, because otherwise we need to compute it as well. So what we would like to do, as I said, we focus on Tvv at the inner horizon. So we already know the bare mode contribution in the Unruh state. We know this piece in terms of things that we can compute. And we would like to find another quantum state, Q, such that this vanishes. TVV at the inner horizon in this other quantum state vanishes. And then we will have a recipe that we can use to compute. Okay, so the motivation for finding this other reference state will be, if you recall, I told you that TUU in the Unruh state at the event horizon, which I denote by plus, vanishes because of regularity of the Unruh state at the event horizon. So that is a motivation. And it has the following bare mode contribution. Okay, over here. And now we are motivated by this, and we would like to ask, can we construct a quantum state, which we call U underbar, such that just like TUU plus in the Unruh state is 0, TVV minus at the U underbar state will be 0. TVV in this new state will vanish on the Cauchy horizon. That's what we want. So let me illustrate how we are going to find this, to construct this other state. So again, we want TVV at the vicinity of the Cauchy horizon, which we denote here by C. And the Unruh state is defined through the red frame. But it turns out that the metric extends through the ring singularity to negative R values, all the way to R goes to minus infinity, which is in fact an asymptotically flat universe. Just like A is the asymptotically flat universe at R goes to infinity, we call this A bar, the asymptotically flat universe at R goes to minus infinity. And we would like to treat this blue frame based on A bar, just like we treat the red frame based on A. Okay, so because R goes to minus infinity at this A bar domain, we are motivated to make a coordinate transformation between R to R bar, which is minus R. And then we also do, we also define a new mass parameter, which we call M bar, which is just minus the original mass parameter. And if we, I'll do this animation again. If you look at the metric and now I put bars on every R and M, it just stays the same. So that means that we can treat the blue frame just like we treat the red frame with these new parameters, R bar and M bar.
I'm sorry, actually I missed the definition of underbar, and this is different from this the upper bar and the underbar. The definitions are different, or there is some kind of relation.
Oh yes,
the previous
we're going
page.
to get to it. Yes, we are going to construct the U underbar.
Yeah, this one. Yes. Actually,
yes,
I'm sorry, but I missed the definition of the underbar. So.
Oh, you didn't miss it. We didn't yet get to it. I was just giving the motivations.
Okay.
Yeah. So we would like to construct U underbar such that it has this following property, and now we are going to do it.
Oh, I see.
So
sorry.
Yes. So we are going to do it in two steps. Okay. First, we look at this blue frame, and the blue frame is just like the red frame. Not exactly, because it has a singularity, it has some other features, but we treat it carefully and similarly to the red frame under this mapping that R goes to R bar and M goes to M bar, which is just the minus original mass. So that means we have a repelling universe rather than an attracting universe over here. And this blue frame also has an event horizon in a sense, or a black hole. So this is an event horizon, this line over here, in a sense that if we send signals from below it, they reach infinity at R goes to minus infinity. And if we send signals above it, they don't reach infinity. So then in the blue frame, we can also define horizons in this way, using this very metric. And all the asymptotic domains that exist in the red frame also exist in the blue frame, but in an analogous way. So we put a bar. So we have the event horizon bar, and the IH bar, and the PNI bar, and so on. So that's just to build an analogy between these two domains. And there are some more relations relating the blue frame and the red frame. They can be easily derived by looking at the metric and using this transformation. Okay, so that's just to introduce the negative mass universe, because we are going to need it. So at the first step, we construct a U bar, not yet U underbar, but U bar state in the blue frame, which is analogous to the U state in the red frame. After we have received an analogy between the blue and the red, we can also create an analogous state. So just like the U state was defined with boundary conditions on these asymptotic surfaces, the U bar state will be defined with initial conditions on these asymptotic surfaces. So again, it's just very analogous. And I will just note that in the blue frame, there is no Cauchy evolution because there are closed time-like loops. But this doesn't pose a problem because we can decompose the initial data in terms of modes, and the individual modes don't see any problem. The radial equation is smooth throughout the singularity, and we can evolve each individual mode in a well-defined way. So that's how we define the U bar state in the blue frame. So why am I doing all this? Why am I telling you all this? Again, recall our motivation. We said that TUU in the Unruh state, which I denote by red everywhere, vanishes at the event horizon. Okay, TUU in the Unruh state vanishes at the event horizon. And now I look at the small vicinity of the event horizon, I call it epsilon. And it had the following bare mode contribution. Now, as I was talking about the analogy between the red and the blue, we would like to go from U state to the U bar state. So that takes us from this epsilon vicinity to an epsilon bar vicinity. Epsilon is just above EH, so epsilon bar will be just above EH bar. And the U direction maps to the U direction. So that means that TUU in the U bar state is 0 at epsilon bar, just like TUU in the Unruh state was 0 at epsilon. And it has the following bare mode contribution, which is just taking this expression and applying the dictionary between the blue and the red frames. Okay, that's not bad, but it's not yet what we wanted, because what we wanted was to find TVV at the Cauchy horizon vicinity. So how do we get from this epsilon bar to this C domain over here? So what we are going to do is time translation. We take epsilon bar to C by doing a time translation of this entire blue frame through this dotted line. And when we do that, we get the green dashed frame over here. Okay, it's just the time translation. I'm sorry, the time reflection, not translation. The time reflection of the blue frame. So that takes epsilon bar to epsilon underbar, which is exactly this C domain. So we define the U underbar state to be the time reversal of the U bar state. Okay, it exists in the green frame. So now when we take U bar to U underbar and epsilon bar to epsilon underbar, just by reflecting through this line, we get that here at epsilon underbar, which is just the Cauchy horizon vicinity we were interested in, we get that TVV vanishes there. Why TVV and not UU? Because U translates, this U direction translates to this minus V direction through the time reversal. Okay, great. So this is an illustration of how we construct our states. And we find that TVV at the Cauchy horizon vicinity is 0 in the Unruh underbar state, which is exactly what we wanted. And it has the following Baire mode contribution, which we again found by this dictionary. So that's great. It's quite simple. So again, we wanted TVV at the inner horizon in the Unruh state. And we wrote it as the difference between the Baire mode sums plus TVV at the Cauchy horizon in the U underbar state. But we know it is 0 by construction. So that's very good. We are just left with this difference. And these are two expressions we saw before. TVV at the inner horizon in the Unruh state has this form, and TVV at the inner horizon in the U underbar state has this expression. And that's very good because all the components in this recipe, all the ingredients, are things that we can compute by solving simple ODEs. These are the rho, the reflection coefficient for the up modes outside the black hole, A and B, which are the coefficients of the asymptotic form of the radial function inside the black hole at the inner horizon, and the spheroidal harmonics. And all of these may be computed numerically, and our colleagues Mark Casals and Adrian Otto are very efficient at doing that. So how do we perform the computation of TVV? We are already very close. We do it in a mode-wise way. So that's how we do the regularization. We take the Baire mode contribution in the Unruh state and the Baire mode contribution in the U underbar state. We subtract them mode by mode, and then we sum and integrate. So each of these diverges when we sum and integrate. So a very important test would be, is the difference indeed regular? And indeed we find empirically by performing the computation that not only it is regular, this difference, but we find exponential convergence in both L, going to large L, and in both omega. So that is very good news for the numerics, because it means we don't need many to compute many modes in order to perform this computation. So that's our recipe. And just to complete it, so far we talked about TVV. That's our recipe for TVV. And to find TUU, we recall that they are related by a conserved quantity. And it is given this way in a mode-wise fashion. And the difference between TUU and TVV, you can note that it only depends on the outside of the black hole. That is, because it is a conserved quantity, it is independent of R. So it only depends on the reflection coefficient. Okay, good. So now we have our recipe for computation. We constructed a quantum state in order to use simple state subtraction. And now we can apply these expressions that I showed you, this recipe with its ingredients, to find actually numerical results. So we start at the pole. We start at the pole because it turns out that at the pole only m equals 0 contributes because of how the spheroidal harmonics behave at theta equals 0. So that is easier to compute numerically. So what we see here is the inner horizon fluxes, the Cauchy horizon fluxes at the pole of Kerr black holes of various spin. So we vary the spin. We computed between 0.55 up to very close to 1. And we see that as we decrease the spin, it is closer to Schwarzschild, which means that the inner horizon is closer to being the Schwarzschild singularity, we can say. So these are diverging in this direction. The fluxes are diverging in that direction, but in the direction of larger spin approaching extremality, they approach zero. The fluxes approach zero, and here we are seeing zoom on this domain, and we see that actually the fluxes change their sign. So they are positive at smaller spin, but at some critical spin, both fluxes, TVV is the blue, TUU is the red, change their sign. And then they reach a minimal value, and then they approach zero as extremality is approached. So that's interesting and nice. I will soon show you how it is compared to the Reisen-Nordström picture we saw, but just another note is that in this picture, you see that TVV and TUU really sit on top of each other. TVV minus TUU is small. And the reason why it is small, we can say, just trying to explain what we see, is because, again, it is TUU minus TVV is related to a conserved quantity. And this conserved quantity, when we evaluate it at the event horizon, remember that TUU vanishes there because of regularity of the Unruh state. So at the event horizon, this difference is up to a factor that has to do with the R ratio. It is just TVV at the event horizon, and TVV at the event horizon is small because we don't have a large curvature there yet with respect to the inner horizon. So because at the event horizon things are expected to be smaller, that's why TVV minus TUU is expected to be small also at the inner horizon. Again, because it is just TVV at the event horizon. So that's just to try to explain what we see here. Now in the spherical charged case, this is what we found. We also found that the fluxes change their sign at a certain charge value. And these charge values, these critical charge values of sign change, were larger in the Reisen-Nordström case than in the polar Kerr case. Okay, that's just an observation, but the general behavior is similar to the Reisen-Nordström case. And now it's very interesting to also go off the pole and look at other theta values. Reminder that this is theta. So here we just chose one spin. We look at A over M equals 0.8. And we look at it versus the polar angle. Now this is a more difficult computation to do because it requires summing also over all M values. M equals 0 is not enough for this computation. So here we start at the pole. This point also existed in the previous graph. And as theta increases, the fluxes decrease. They cross the horizontal axis, they change sign, and they reach some minimal value. They change sign again, and they reach some maximal value here at the equatorial plane. So this is a picture we couldn't expect. And it's very interesting, but keep in mind it's only for a specific spin. So we plan to perform this computation also for different spins, and we'll see how this picture changes as a function of spin as well. Will we still have this feature over here and crossing the 0 at 2 points and so on? So that is something we are going to do. We already started, but no results yet. Okay, so that's an interesting plot, which has no analogous plot in the Reisen-Nordström case, of course, because of spherical symmetry. So these are the two main plots that I wanted to show you. So, but let's go on, because our method is new, and as you saw, we used a non-standard quantum state. You saw how we constructed it together. It's not one of these standard quantum states that are already known. So we wanted to test our method against other methods. It is very crucial to perform this test to see that we got the right results. So now a standard method for regularization in curved spacetime is point splitting. DeWitt did it for phi squared, Christensen for the stress energy tensor, and Wald and others. And in our group, Adam Levy and Amos Ori, they developed a mode-wise approach to point splitting, which is what we use. But we don't know how to do point splitting straight at the inner horizon, because the counter terms diverge there and bad things happen. So what we're going to do is use point splitting to compute the fluxes on approaching the inner horizon and see what we get. So this is what we get. These are the point splitting results on approaching the inner horizon values. So the horizontal axis is the log of the difference between R and R minus. So this is how close we are. The inner horizon would be infinitely to the left. So the dots are the point splitting results, and the horizontal lines, both for TUU in red and for TVV in blue, are the inner horizon values, which we computed using state subtraction. And we see that for this specific case of spin 0.8 and on the pole theta equals 0, we find that the point splitting results approach very well up to 4 or 5 figures the IH values computed in the other new method, which is state subtraction. So this is reassuring. We also computed the fluxes between the horizon, not only at the inner horizon, but between the horizons. But this is still preliminary. We are working on a paper on that now, on how the fluxes behave between the event horizon to the inner horizon at the pole. But that's just a taste. And another thing that we did, as I showed you in the preview, in the first graph, we saw that the fluxes approach 0 when extremality is approached, when A reaches M. So we were interested in looking at that limit more closely. So we can define epsilon as being the difference from extremality, because A goes to M is extremality. So in the near extremal case, we have very small epsilon. And now analytically and numerically, we found that TVV at the inner horizon at the pole behaves like epsilon to the 4th. And we also found the coefficient analytically. And numerically, and not analytically, we also looked at TUU at the inner horizon. It goes like epsilon to the 5th. And that means that the Hawking out flux, remember this conserved quantity, TUU minus TVV, that means that the Hawking out flux is dominated by the TVV component in this limit of approaching extremality, and it has this form. So that's quite interesting. So this is the Hawking out flux per unit solid angle in the polar direction. It behaves like this when epsilon goes to 0, when extremality is approached. And here is just a nice graph to illustrate that this is indeed what we see numerically. So all the points here are numerically computed. And the horizontal lines are the analytical results in this case. And in this case of TUU, we don't have an analytical result, but here we see them all on the same graph. The red is times epsilon to the -5, and the green and blue are times epsilon to the -4, which are the corresponding powers. And again, this is as a function of the log of the small parameter. So that's nice, and you can see that in the supplemental material of our paper. And we also have very similar results in a Reise Nordstrom, in which we wrote a paper on near extremality, a PRD. Okay, so these are the numerical results. There's still a lot more to do. I'll talk about that in the summary. But now let's have a very preliminary discussion on back reaction. What the results we found may mean for the Cauchy horizon itself, for the geometry of the black hole through the Einstein equation. So as I told you before, just like TUU being non-zero at the event horizon would mean a singularity at the event horizon, TVV being non-zero at the inner horizon implies a curvature singularity at the Cauchy horizon. And again, this is because we transform to the Kruskal coordinates, which are regular, and dv to dv diverges, right? Because v goes to infinity at the Cauchy horizon. So if TVV in Eddington coordinates is non-zero, we have this diverging factor over here, which drives it to infinity. So that's a curvature singularity. But I would just like to note that this curvature singularity is on the classical background, the original background, where v goes to infinity, because if we take into account evaporation of the black hole, v doesn't go all the way to infinity. It just becomes very, very large. So that's just the first step in the back reaction. Now, in the spherical charged case, we saw that just looking at the Einstein equations and doing some and neglecting some terms, we got that r comma y, the way that r changes in the y direction, which is either u or v directions, it equals to minus some factor times tyy, the flux component, the corresponding flux component at the inner horizon. And this is in accordance with the Ricciarduri equation. So that means that r comma v, the change in that direction, goes like minus tvv that we computed at the Cauchy horizon vicinity, and r comma u would go like minus TUU in the Cauchy horizon vicinity. So that means that the sign that we found of the fluxes has a very strong effect on what will happen both to our traveler in terms of tidal deformation, which is dominated by TVV, and what will happen to the Cauchy horizon itself, which is a harder problem because it's already deep in the back reaction question. So the sign of TVV will likely determine the nature of tidal deformation. Even if the black hole hasn't changed much from a Kerr black hole, we still have a very big domain where tidal deformation occurs because of this exponential factor over here. V changes very rapidly. So an infalling observer will undergo abrupt because of this factor, expansion or contraction. It depends on the sign of TVV. And you can see it through this equation, which looks at dr to d tau, which goes eventually like minus TVV at the Cauchy horizon times this diverging factor. And the sign of TUU at the Cauchy horizon might determine the fate of the Cauchy horizon itself. But this I don't want to say anything about because we still need to look at it more deeply and see how this happens. But everything I said here is just things we saw in the spherical charged case and requires further investigation in Kerr, which we want to do in the future. Okay, so now just to summarize what we did so far. So we constructed a very unusual quantum state, a new quantum state. We called it U underbar, and we used state-subtraction with this U underbar state to regularize the fluxes and compute them in the Unruh state at the inner horizon or at the Cauchy horizon. Now, we found when we numerically applied this method that TVV and TUU at the inner horizon in the Unruh state both have well-defined and non-vanishing values, which in itself, it's very important because that means the TVV in Kruskal coordinates at the inner horizon diverges, and we have a curvature singularity. And the sign of the fluxes, we also saw that it changes, and it depends on the spin, and it depends on the polar angle, and the fluxes change their sign. And we saw that both fluxes vanish at different rates as a function of epsilon, as I showed you, as extremality is approached. And we compared against point splitting results, at least at the pole. We should also do it off the pole. And we got excellent agreement between the two methods. So in the future, so our main motivation for asking this question, like the story I opened with, is back reaction. Is the Cauchy horizon traversable? So this is something we would like to get to eventually. But there are also several extensions we can do to this work in the numerical level. So far, we use state subtraction at the inner horizon. And we looked at only two lines in this two-dimensional plane. We only looked at the pole at a certain spin, 0.8. No, I'm sorry. We only looked at the pole at a variety of spins, and we looked at a certain spin, 0.8, as a function of the polar angle. But we would like to draw more lines on this two-dimensional plane. And we also have a third axis, which is things we can compute via point splitting, going off the inner horizon and to other R values. And that I only showed you for 0.8 and on the pole, how the fluxes behave between the horizons. And we also did it, I'm not showing it here, but we also did it for 0.9, also to check how our method works, but still only at the pole. And we would like to go off the pole and see what point splitting gives us. But that would be very hard numerically, because on the pole, we only need to compute m equals 0 modes, and off the pole, we need all the modes. And L can get quite large, and so M multiplies everything. So that's a hard task, but it is something that we would like to do. And of course, more physically realistic would be to leave behind the quantum scalar field case and go to the quantum electromagnetic case. I don't know if I will do it, but it's important that someone will extend this work in this direction. So that's all for now. Thank you very much for listening, and again for inviting me. And if you would like to read more, so this talk was based mostly on a PRL, which was very recently published. You can find it on arXiv. And if you would like to contact me, that is my email. So I will stop sharing now, and
thank you.
Open for questions.
Okay, thank you very much for your wonderful talk. And now let's take the questions.
I have a questions if you allow me to ask.
Yes, please.
Yeah. Honestly, I'm an outside of your field, but I work on classical self-force problems, and part of your analysis actually looks very much analogous to the regularization procedures they use in self-force calculation. So did you get the idea, like the renormalization of this TUV, TUU, TVV from the idea of the radiative field in self-force, such as half advanced and half retarded field, subtraction between the two quantities, such that you don't have to deal with the singularities of the, the point where you want to evaluate the quantity.
So if I understand correctly, you ask whether we looked at methods that are used in the classical problem of radiation reaction
Yeah,
of the
that's
cell
right.
force?
Yeah.
Yes.
Because I mean, I recognize some of your collaborators actually, that I find in the cell force community, such as Mark Kazar and the Otuel, and the UO method looks very much similar to the method they use in the cell force. And
yes, it's these problems are indeed very much related, and these two communities working on semi-classical effects inside black holes and the community working on self-force very much related. I personally have no experience in the self-force problem, so I don't know if I can really answer this question, but and also my advisor, I don't think he has much experience with the self-force problem, but our collaborators, Mark Casals and Adrian Otterwill, do. But the methods that we use are methods that are well known within the semi-classical community. State subtraction as well as point splitting are methods that are used quite extensively. So these are the methods that we use, but they might really have an analogous in the field of self-force.
Is your advisor Professor Amos Ori?
Yes.
Okay. So yes, it's not surprising that you share the same method as self-force community.
Yes. Yeah.
Yeah. So another question is, in the classical self-force problems, people actually are concerned about the gauge issues. It's very serious because depending on the gauge, your computational results actually vary. But here you deal with the scalar field as a constituent of the the matter, but this is not just the field itself. You actually contract the field, to form to construct this energy momentum tensor. That means, I mean, the geometry actually is involved there. But are you completely free from these gauge issues? Because geometry is involved in the field.
I'm actually unaware of any gauge issues.
Okay.
I know that there exists an ambiguity, especially when it's not vacuum. There exists an ambiguity in the counter terms that we use, and but here it's vacuum. So I'm actually not sure if you can. I would like to read more about that. If you can maybe send me to some paper that I can read about these gauge issues, because I'm unaware of them.
Okay. But I mean, it's known that scalar field and electromagnetic fields actually you don't have to worry about the gauge issues. But with the gravitational field, you do have to actually worry about.
Oh yes. Okay. Now I understand.
Yeah, but the construction of this energy of the tensor actually requires geometry. I mean, the knowledge of the geometry where you compute the quantity. So I mean that was my question. Whether this issue is important or not.
Yeah. So actually, me and Amos just talked about it quite recently, about what will happen in the gravitational case when we take, instead of a scalar field, we take a gravitational perturbation. And what we think so far is that indeed there is a gauge issue in the local sense, in the local back reaction effect, but the dominant back reaction effect is one that is carried on a long time scale. And from what we think so far, from what we've seen very preliminarily, the gauge issues should not affect this long time effects.
Okay.
Only the small local effects. But that is a very interesting issue in the gravitational case, yes.
Okay. My last question is, so you're dealing with axis symmetric space-time anyway, and and you have to actually take care of this the angular dependence, which is in fact requiring the spheroidal harmonics decomposition. And but my question is, how do you get this equation for the angular dependence? I mean, do you solve Tukolsky equation, or do you solve Einstein equation directly? To find this angular dependence.
The angular dependence.
Yeah.
Well, we just need to solve. So as I showed, we take everything and we decompose it in modes before we even do any computation.
Yeah.
And this mode decomposition, as you say, has an angular dependence on spheroidal harmonics. And the spheroidal harmonics solve this equation that on Mathematica, we use Mathematica for our computations, Wolfram Mathematica. It knows how to solve it. And also our colleagues know how to solve it, but I'm unaware of the exact details of how they do it. But numerically, it is possible to solve for the spheroidal harmonics for each omega LM mode. And then, of course, we sum over all modes. So it's just a numerical computation. It's an eigenvalue problem.
But my question was actually where you get this equation for the angular dependence. Normally, I mean, you that comes from the equation, the very basic equation, like Einstein equation or Tukolsky equation. But where do you get the?
Yes.
Do you solve the
it
Tukolsky
comes
equation
from
in the spin zero? Or?
Right. It comes from the Tukolsky equation. The way I think, I think Tukolsky, maybe even Carter before him, I'm not sure actually, showed that this equation for the scalar case is decomposable, and the radial function solves this equation, and the angular function solves this equation.
Okay.
So yeah, it comes from the decomposition of the Tukolsky equation, of the wave equation.
Okay.
Yes.
And of course, you don't have to worry about the radial dependence there, because you probably you fix the radial point, right? And such that you have, you just deal with only angular dependence there.
We do have to solve the radial equation because our final recipe had ingredients which are the reflection coefficient outside the black hole and the coefficients of the asymptotic behavior of the radial function inside the black hole. So one way to find these coefficients is to just solve the radial equation. But our colleagues, Marcus Sals and Adrian Otto, will have a method, an MST method, which, so they know how to find these coefficients to very good precision without actually solving the radial equation.
Yeah, okay. Yeah. So you use a semi-analytical approach developed by the Japanese people in the 80s, right? The MST. Yeah, okay.
Yes, yeah.
Okay, thank you very much. Yeah.
Okay,
thank you for your good questions.
And another questions?
I have, simple question. So the question is, what about RM black hole regarding the singularity of the energy momentum tensor at the inner horizon? So you showed only about
I didn't. I can't really hear you.
Okay. Can you hear me?
I can hear you, I think. You're asking what about the Reiser-Nordström black hole?
Yes. So regarding the singularity of energy momentum tensor at the inner horizon. So whether it is the singularity?
Yes. So indeed, what we found in the Kerr black hole is quite similar in many ways to what we found in the Reiser-Nordström case. at least in polar care, actually the equations we get for care at the pole at theta equals 0 are quite similar to the ones we get in Reise-Nordström. So indeed, the results were also quite similar. I will share this graph again, just a second. Okay, I just want to share this graph that I showed. Yeah, so here we saw for the Reise-Nordström case, we saw that we got the fluxes also are non-zero and also change their sign and also approach 0 as Q goes to M, like in the care case when A goes to M, at least in the polar situation. So, and then when we use the same back reaction preliminary discussion, we find the same sort of singularity, because the relation between the Eddington V coordinate is like to the Kruskal regular V coordinate is very similar in care and Reise-Nordström. So the singularity in terms of this coordinate is just the same, actually.
Okay.
But we actually, we looked at it more deeply in Reise-Nordström than in care. We still need to complete the discussion in care.
Okay, thank you.
Thank you.
Okay, another question.
Can I ask a simple question?
Yes.
Is there any intuitive explanation for the sign change of the stress tensor?
That's a nice question. So I will share the screen again just to show this graph. Just a second. Okay. So do you see the graph?
Yes, yes.
Okay. So there are a few things that we can understand intuitively and other things that I don't know how to understand intuitively. Maybe someone else knows. But so there are a few features here. The fact that the fluxes are diverging towards, they seem to be diverging towards a smaller A over M or smaller Q over M in the charged case is intuitive because we are closer to Schwarzschild, where there is no inner horizon, but there is a singularity up there. But the sign actually of this divergence is not something that we can expect, I think. Another thing that we can expect intuitively is the way that the fluxes approach 0 as extremality is approached. The way that we understand it intuitively is because in extremality, the event horizon and the inner horizon are together. So as we approach the extremality, the interior of the black hole gets smaller and smaller, gets narrower and narrower. So there is not much, and the potential also decreases accordingly. So there is not much dynamics going on. And in the Unruh state, as I said, the event horizon is regular. So that's why we expect that as we approach the extremality, the fluxes to accommodate for this regularity would need to vanish. So these are two things that we can say intuitively, what happens near extremality and what happens at very small spin. What happens between these two extreme cases is not something that I am aware of how to explain intuitively. Yeah, I would say it was not expected for us in the Reise-Nordström case, but once we saw it in the Reise-Nordström case, we expected that in the care case it will be similar. And I think this is also shared by, this view is also shared by Amos Ori, my advisor. So it's generally a good question. we could ask, why would it be positive? Why would it be negative? We can't really answer this question. And why would it change at a certain point? So yeah, it's a very good question. We still don't have an intuitive understanding of it. We just think we understand the limits of the range, but not this middle range where things actually change.
Thank you.
Well, I'm Kwon Kang. The negative flux implies some energy flux having negative sign or negative energy flux outside the passing the inner horizon. Is that the correct interpretation of the negativeness, the sign change?
Yeah. So at the event horizon, it is true that TVV is negative in the Unruh state. At the event horizon, TVV is negative and Tuu vanishes in the Unruh state because the Unruh state corresponds to an evaporating black hole. Okay. And that also relates to the question of the previous person, that we do know that TVV is negative at the event horizon, and then it's a question what happens between the event horizon and the inner horizon. So when we are close to extremality, this TVV, which is negative at the event horizon, doesn't have much time, space time to change, so it stays negative. And now regarding the interpretation of what TVV means, negative TVV at the inner horizon vicinity, you were asking about some flux crossing the inner horizon. Well, because TVV is non-zero there in Eddington coordinates, that means the TVV in regular coordinates, the Kruskal coordinates, is diverging. So we actually think a singularity forms there. So if a singularity forms, there is no flux crossing this surface. But in the bigger picture of back reaction, we might find other things. But this is a bigger question.
But this sign change happens only for certain value of spin parameter.
Yes.
Not for any spinning black hole, right?
You mean a sign change as a function of what?
Function of A, the spin parameter.
Yes, we saw a sign change. So
only for certain
we saw a sign change.
large values of A over M.
Mm-hmm.
So if
yes.
The curve black hole is slowly rotating, and there is no sign change, right?
That's true. If the black hole is slowly rotating, and again, we only looked at this at the pole, so I have to say that. But if the black hole is slowly rotating, then we do expect that, as we saw, the fluxes will be positive.
So do you think for a slowly rotating case where the flux is always positive along the polar angle, polar direction, will it be there some angle where the sign flux becomes negative, even for that case?
That would be very interesting to look at. Yeah, we still, so as a function of the polar angle, we only looked at one spin value, 0.8. But as we saw, as the spin is lower, the value at the pole is larger. So in order for the sign to change, there would need to be a lot going on, I would say. I mean, it would need to decrease very rapidly as a function of theta to reach the horizontal axis. So I would guess that maybe it doesn't happen, for slowly rotating black holes, but it's just a guess, and we do need to compute that. Actually, we are actually more interested recently in the other direction, in the other limit, in the near extremal limit, and we started performing a computation as a function of the polar angle there in the near extremal limit to see what happens there, because there we have negative fluxes, and we were interested whether there is a sign change in this negative case. So this is a similar to the question that you are asking in the slowly rotating case. So it's my answer is that it requires more investigation, and we can just guess.
Okay. You guys have any more questions? Actually, I have a few questions. Can we understand the energy flux as some kinds of Hawking radiation inside the black hole? Can you understand like that?
Yeah. Well, when we look at the difference between the fluxes, TUU minus TVV, it is generally the Hawking outflux. When we look at TUU minus TVV at the inner horizon, times r minus squared plus a squared, it is a conserved, it is related to the Hawking outflux at infinity. So doing these computations at the inner horizon, we do get information about the Hawking outflux through this conserved quantity. But can we build some analog when we look at the individual TVV or TUU? I'm not sure what their meaning in that respect would be. I can only look at the difference between them and say this is the outflux, because TVV minus TUU is just TR, right? That's the quantity we're looking at. But regarding the individual TVV or TUU, they have different implications for back reaction, which I very shortly discussed. And their difference is the one that talks about the outflux.
Okay. Okay, thank you very much. And another question?
Well,
no? Okay.
This outflux at the inner horizon looks like some flux coming from white hole horizon, right? So classically there is no such flux, but at the quantum level, you are saying there could be some radiations. Okay.
Yeah, at the inner, yeah.
Okay. I wonder. You showed the finiteness of this regularized flux implies the curvature singularity. But if there is a curvature singularity, then but this calculation is based on the curve background, which is regular at the inner horizon, right?
Yes.
So suddenly this regular space-time becomes singular. Your calculation is based on that, the regular space-time. Only the quantum quantity showed divergence, right? So it simply implies the kind of instability, quantum instability, right? So that does not necessarily means so you claim that if we take into account this bang reaction of quantum divergence, so then the space-time could become singular there, right? Okay.
Yeah, so actually the form of the singularity is still needs to be investigated, because when I said there is a singularity because v goes to infinity there, that would actually not
allowed in
suit
the background space.
Yeah, that's only on the background space. That's only the first step in back reaction. But when we take into account evaporation, which is what we need to do to find the picture, the correct picture of back reaction, we would need to take into account evaporation and a specific model of evaporation. And the specific model of evaporation we choose will have an effect on whether the singularity that is formed is really a strong singularity or a weak singularity, and how is it with respect to the classical singularity that is formed because of perturbations at the Cauchy horizon. So that's a question of taking evaporation and combining it with the fluxes that we found. And that is something that we started looking at, but still it's very preliminary.
Okay, since you mentioned the classical stability, so the Cauchy horizon in the core black hole is unstable. It has the under classical perturbation. I'm just, would you remind me about that fact? So we know Reissner-Nordstrom Cauchy horizon is unstable on the classical small perturbations. What happens to the core case?
To the what? Sorry, in the Kerr case.
In the core case.
Yes. Yes.
It's unstable.
Yeah.
On the classical perturbation.
Yeah, under classical perturbations, there is a weak singularity that forms there. There is Amos Obi work from 1992 about that, about the weak singularity. And what we found in the quantum case is that probably the singularity is stronger than in the classical case, because there is no price law. There is no weakening of the divergence.
That was one of your motivations. The quantum effect is also is not weakening the singularity, the classical singularity, but make it stronger. That's your finding. Okay, that's interesting.
Yes. Yeah.
All right. But
again, it still depends on looking at a specific evaporation model and seeing what it does to the singularity. But generally speaking, yes, we find a stronger singularity in the quantum case, in the lack of a price law.
But you have to see we may guess, we know, we may ask what will happen after the bang reaction, because the rotational energy is finite, right? The core black hole quickly lose its rotational energy due to this quantum instability, and quickly loop becomes not slow rotating or non-rotating. Then it becomes stable, right?
Yes, that's true. If we take such an evaporation model in which the black hole slowly becomes non-rotating, then if we follow this this plot that I gave as a function of A over M, we see that the fluxes change their sign as time goes on, as the black hole evaporates. Maybe they start negative and they become positive, and that means that that has implications for the singularity. We need to look exactly what that would mean through the Einstein equation. But yes, we have to look at the change of the sign as a function of time of evaporation over long times.
Okay.
Yeah.
Okay.
Okay.
I think. Okay. Thank you. And I think we have already 30 minutes past our regular time. So thank you very much, Noa, again.
Thank you
And
very
that's
much.
it
Thank
for
you
the seminar.
for listening, for asking good questions.
Okay. And if you have more questions, then you can continue just for a few more minutes. And our
Yes,
official
and
seminar is over now. Thank you very much.